Sometimes data is not normally distributed, and there's not always a way to correct for the problems of distribution of the data set. So in that case, we use non-parametric tests. These are sometimes referred to as assumption-free tests, but they are not completely free of assumptions. They just make fewer assumptions about the type of data on which they can be used than tests dealing with normally distributed data, or parametric tests. Most of the tests require the data to be ranked, which is when you arrange the scores in ascending order and find the lowest score and give it a rank of 1, then find the next highest score and give it a rank of 2, and so on. If a number is repeated several times, then this is referred to as a tied rank, and these values need to be given the same rank, so you assign a rank that is the average of the potential ranks, or in other words, the ranks the numbers would receive if the pattern continued by adding 1 to each number before it, for each of the scores. The ranking process results in high scores being represented by large ranks and low scores being represented by small ranks. Then you sum the ranks of the group and you have to correct for the number of people in the group. So you subtract the mean rank of the group for a group of that many people. The mean rank is the mean of the numbers that would have potentially been assigned to the number of people. So with 10 people, it would be the mean of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The resulting value is referenced as a W. The analyses are then carried out on the ranks as opposed to the actual data. This process makes it possible to use data that break the parametric assumptions. 4 of the most common non-parametric procedures are the Wilcoxon rank sum test, which is also known as the Main-Whitney test, the Wilcoxon sign rank test, the Friedman's test, ANOVA, and the Kruskal-Wallis test. So the first test I did is a Wilcoxon rank sum test, and the dataset uses 2 different groups of participants, one receiving and experiencing a bonus and the other receiving and experiencing a vacation day, to see the effect the gift had on job satisfaction scores. 10 participants received the unexpected bonus, while the other 10 participants received an unexpected vacation day. The scores were measured on a 1 to 20 scale and taken the day after receiving the gift and again the day after experiencing the gift. In other words, the day after the bonus was put into the participant's account, and the day after the participant had used the extra vacation day. I used the Wilcoxon rank sum test because I had different participants taking part in 2 different conditions, and hypothetically my data violated an assumption of the independent t-test. The Wilcoxon rank sum test is also referred to as the Mann-Whitney test. They are the non-parametric equivalent of the independent t-test. The test compares 2 conditions when different participants take part in each condition, and the resulting data violate any assumption of the independent t-test. We can tell if the 2 groups are significantly different by looking at the p-value and seeing if it's less than 0.05. So first I started by installing the necessary packages. We're going to get this message over and over again because it's going to ask you to restart it, and then also I've probably already libraryed a lot of this stuff before, but for the sake of this, we're just going to do it. Is it done asking me? Okay, now here's where I technically library it. It's already been libraried. The ClinFun package would be used for the Jock-Keir test, which I'm not doing. The PASIX package is used for descriptive statistics. The Pigermus package is used for post hoc tests, which I'll discuss later. And ggplot2 is used for graphs. Librarying them makes it so that they stay in your R. This is where I would attach the data set, which I've already done. Now, this is where we get into the good stuff. This is where I created a data set in R that mirrored the data set created in Excel so that R would run correctly. The data was collected using different participants in each group, so I had to input the data using a factor variable. I created the variable called gift using the GL function, which contained 2 blocks of 10 rows of data, which is what I'm doing right now. The first block was labeled bonus and second is labeled vacation. Then I created the second column of data, which has the values for my dependent variable of job satisfaction scores measured the day after they found out they would be receiving them, which is called JSS score RG. And then the scores measured the day after they experienced these gifts, which is called JSSEG. And then I binded them together to create a data frame called JSAT data, which is what I used throughout the video. Next, I ran exploratory analyses to see on the data to see the group differences. The first code reports the descriptive statistics and tests for normality because I included norm equals true in the line of code. The output tells me that we're receiving gift data, which is in this column. For receiving gift data, the distribution for bonus, P is greater than 0.05, W equals 0.93, so the distribution for gift data for bonus appears to be normal, and the vacation data are also normal, with P is greater than 0.05 with 0.65, or 66, excuse me, and W equals 0.95, and I can tell this by looking at the significance of the Shapiro-Wilk test to see if the value is less than 0.05, and if it's greater than it, then it's not significant, which these were not. Then for the experiencing gift data, the bonus is also normal with a p-value of 0.2, W equals 0.9, and the vacation is also normal with a p-value of 0.5, W equals 0.94 right there. Although all of my data is normally distributed, if I had seen both non-significant and significant p-values throughout my data, then it would tell me that the sampling distribution might be non-normal or not normal for the data, and that a non-parametric test should be used. I then ran a Levine's test, which is what I'm doing right here. And we'll go ahead and run the other one as well. The second one was on the experiencing gift data, and the first one's on the receiving gift data. And this looks at the homogeneity of variance for the data. For the receiving gift data, there's 118 degrees of freedom, which you see right here, with a F value of 0.04 and it's non-significant with a P value of 0.84. And for the experiencing gift data, there's again 1 and 18 degrees of freedom with the F value of 0.48, and it's not significant with a p-value of 0.498. The variances are not significantly different, indicating that the assumption of homogeneity has been met. You know what I mean. Next, I ran the Wilcoxon test, which uses the Wilcox.test function and can be done in two different ways depending on how your data is grouped. Because my data is stored in a single column, I did the first example of the Wilcox function, which works like the function for running a regression in R. First, I create a new model with the outcome listed first in the predictor, which tells us to which group a score belongs, and the name of the data frame containing the before-mentioned variables. The first model was used to compute a basic Wilcoxon test for the receiving gift data, and the next one was for the experiencing gift. The model predicts receiving gift and experiencing gift job satisfaction scores from group membership. I executed the name of the created model to see the associated output. So here is where I create the model for the receiving gift, and here's the output for receiving gift. Here's where I create it for experiencing gift, and here's the output for experiencing gift. I left all of the default options as R has them for the creation of the model. For the job satisfaction score after receiving gift, the p-value is 0.91, right here, with the continuity correction, which was used because of the default settings of the test. The results tell me that the type of gift, so whether it was a bonus or a vacation day, did not significantly affect job satisfaction scores the next day. W equals 52, P equals 0.91. The next test was for experiencing gift data, and it also showed that the type of gift did not significantly affect job satisfaction scores the next day after experiencing the gift. W equals 46, p-value equals 0.79. So now I'm looking at the effect sizes so that people have a standardized measure of the size of effect I observed so they can compare it to other studies. The created code gets the effect size from the models I created earlier. The next function reports the effect size for the RG model, and then the next one reports it for the EG model. So receiving gift is first, and then experiencing gift is second, as it's been throughout this. So here's where I create the function for it to look at the previous models. Here's where I do it for receiving gift. Here's where I do it for experiencing gift. And so it has the name of the model first, and then the total sample size, which is 20, because that's how many participants are involved throughout the whole study. There were barely any found effects, with a very tiny effect size being found of 0.03, which you see right here, for the receiving gift, and 0.06 for experiencing gift, which is right here. So that is the end of that test, and now I'm going to switch data sets to do Freeman's ANOVA. It's a non-parametric counterpart to the one-way related ANOVA that could be used to test differences between several related groups. If you have data that is violating an assumption, then this is a useful way to get around the problem. It is used for testing differences between conditions when there are more than two conditions and the same participants have been used in all conditions. Like before, this test is also conducted on ranked data. So my research question is, I looked at how a reminder to write down their goals affected task performance over a 3-month time span. I had 10 participants that had not been receiving a reminder about their goals. They then received 2 reminders a week for the first month, and then the same participants continued to receive 2 reminders a week for the second month. The participants' task performance score was measured before they began the study, so when they were not receiving any reminders, after 1 month of receiving the reminders, and then again after 2 months of receiving them. The score was on a scale of 1 to 10. I used a Freeman's ANOVA test because I had the same group of participants involved in more than 2 conditions, and the data did not meet all of the necessary parametric assumptions. So first I created a variable called start with the correct values associated for each participant. So it's their task performance scores before they began the study. Next, I created a variable called month 1, and it contains the scores received for each of the same participants after being reminded of their goals for a month. The next one is called a variable called month 2, which contains the scores for the same participants after being reminded of their goals for 2 months. Then I bind all of these together to form a new data frame called reminders data 23, which is right here. It just puts all the columns into one data frame. I then run some exploratory analyses using the stat.desc function. The results tell me that the Freeman's ANOVA, which I do right now, the results tell me that the Freeman's ANOVA is not significant for the baseline data, which is called start. W equals 0.87, P equals 0.12. It'd actually be 1.1, excuse me. Or for the month into receiving the reminders, W equals 0.95, P equals 0.66. Or for after receiving the reminder for 2 months, W equals 0.88, P equals 0.14. Therefore, none of the variables involved differ significantly from normal. So basically my data is normal, but we're just going to act like it's not. So then I conduct Freeman's ANOVA using the Freeman.test function. The test is very high maintenance and requires that you give it a matrix rather than a data frame, and it wants all the variables of interest in one data set. It will not run unless these conditions have been met. I use the as.matrix function to convert my data frame into a matrix, and because my data frame only contains the variables I'm interested in, I didn't have to do any converting to satisfy the second requirement of the Freeman's ANOVA. The function also gets confused by missing data, so if I had a dataset without a complete set of scores, I would easily delete any cases that weren't completely full of info by using the na.omit function, but my dataset was complete. Let me run it. We are most interested in the test statistic, which R calls a chi-squared rather than F. The test tells us that there is no evidence that goal reminders have any effect on task performance, so the scores did not significantly change over time. And the chi-squared equals 0.16, P equals 0.92. It also tells us that the degrees of freedom is 2, right there. Because there was not a significant overall effect from the Freeman's ANOVA output, I would not normally conduct any post-hoc test. But if it had been significant, then I would use the Freedman MC function to do it, which I attempted to install the packages and the package of Piggermus, which is necessary for it, from the website. That will not run on this version of my R, but that's what I would do if I wanted to install it, and that's how I would library it. And then the Freedman MC function allows for us to compare the groups to a baseline or the starting point. As before, this function also requires for a matrix instead of a data frame to be used, so I would use as.matrix. In order to attempt to do this for you, I installed and libraried the necessary package, but my R was not able to run it. The code that should have been used was typed for you to see, which you can see for all of this. To interpret the output, if it had run correctly, I would look at the column labeled differences. If the column said true, then the groups would differ significantly, but if it said false, then the groups would not differ significantly. As far as effect size go, for Freeman's ANOVA, there isn't an easy way to convert a chi-square statistic that has more than 1 degree of freedom, which mine has 2, to an effect size of R. And also, it isn't that helpful to have an effect size for a general effect like that tested by Freeman's ANOVA. So it is not run. And that is everything for today.